Hey everyone, thank you so much for joining today. It's great to be here. Hope everyone's doing well. Great to see everyone in the chat. My name is Julian Miller, and I've been at DigitalOcean for, I guess, just under 3 years now. And I don't do much game development anymore, but in the past, I've worked on a couple AAA titles, and I wanted to share a little bit of that with you today. All right. So, a natural place for us to start is to talk about how video games work in general. And I guess I should point out that if anyone does have any questions throughout the presentation, I will be stopping at specific points. So if you can hold your question until then, it would be much more helpful for me, and I'll be able to actually catch it then and hopefully respond to you. So games are essentially just ordinary programs that run in an infinite loop. And when you think about a video or an animation, it's really just a series of images that are played back to you quickly, one after the other. So you get this illusion of movement, so something moving across the screen or some action being performed. And video games work similarly, but instead of having a set of pre-made frames, we actually draw each frame in real time just before it's presented to the player. So in this loop, we need to do a few things. And the first thing is to process player input. So this usually comes from something like a gamepad or a keyboard and mouse. And a lot of consoles now even have motion controls. I don't know if has anyone here played Just Dance. That's an interesting one with it capturing your movement. Good workout too if you haven't played it. So the game then processes that input, then updates the game state. And in this step, this is usually where things like physics calculations happen and collision detection. And then with that updated game state, we then draw it to the screen. So then we get our frame that we display in our animation. So ignore for a second here that I skipped from 1 to 3. But just to summarize this video game loop, we process user input, update the game state, and then draw the game state to the screen. And this sequence of events happens over and over, typically 60 times per second, but sometimes it might be more, sometimes it might be less. And yeah, so that's essentially how video games work, in a nutshell anyway. But if we're developing a multiplayer game, we need to add an extra step here. And that's because we need to incorporate other players' information. So not only our own input, but we need to know what other players are doing as well. And we also need to inform other players of what we're doing. So that's where another step comes in, and that's to process network messages. So typically what happens is you're playing a game on some game client. So that game software might be running on a computer, could be running on a console or your mobile phone. And that client is connected to a server somewhere. And then that server is going to be running its own game loop and sends messages at some interval or on specific events. And that server could be a hardware machine, it might be a virtual machine, so say like a droplet on DigitalOcean, or even something like a Kubernetes cluster. And these messages are generally instructions to update the game's client state. So in this example here, we're sending the position of the player to other clients. Other things we might be sending are player score, player health, player velocity, so how fast they're moving. And these messages are usually sent over UDP rather than a TCP connection. Now, I want to keep this presentation as inclusive as possible for people with different backgrounds. So for those who aren't familiar with UDP and TCP, both are essentially protocols for transferring data over the internet. And one of the main differences is that messages sent over UDP aren't guaranteed to arrive at their destination in order. And in fact, they aren't even guaranteed to arrive at all. TCP, on the other hand, gives us guaranteed order and delivery of messages. So a person might wonder, if we're making a game, why not use TCP, which gives us these guarantees? Well, unfortunately, it turns out that the way TCP works makes it relatively slow for transferring small packets of information. And as an example, let's say I have a bunch of letters that I want to mail to my friend Ben, who lives in Chicago. I'm up in the Toronto area, so it's not too far from me, but it'll take a little bit of time for it to get there. And let's say that I want to guarantee that these messages, they arrive to him. I want to guarantee that they arrive to him. And I also want to guarantee that they arrive in a specific order. So what I can do is I can send him the first message and then wait for him to mail me back acknowledging that he received it. And then I send the next one, wait for him to message me back saying that he got that message as well, and then repeat for the rest. And let's say I don't hear back from him on the fourth message, so I end up waiting for a while. Then I wait a little bit longer. And then finally I say, well, maybe he hasn't got it, so then I rewrite the message and send it to him again. And you'll notice that with TCP, in this example, I'm doing a lot of waiting. And in real-time video games, we don't want to be waiting for this information to be sent. So that's one of the reasons we use UDP. So TCP is great for transferring large videos, websites, emails, and those sorts of things. But when we want to send small packets of data immediately, so if we want to update someone's, their player state, UDP is generally better. But one thing to remember is that it's not necessarily a one-size-fits-all kind of thing in game development, especially. So let's say we were making a real-time strategy game or something like chess, where it's a little bit more slow-paced, then UDP might not necessarily be the best option. TCP might give us everything we need. So since we're using UDP, these messages might arrive in the wrong order. And you can imagine that if we're sending these messages to the client, say for an object's position, if they arrive in the wrong order, suddenly I'm going to be moving backwards rather than moving forwards. So to get around this, most game engines actually have a thin layer built on top of UDP, and that will guarantee that messages are sent in order. So now we have a fast protocol with guaranteed ordering. But what about guaranteed delivery? So in most cases, you would think that we probably want to make sure that our messages are getting to where they're supposed to go. But for some things, it actually doesn't matter. So for example, hopefully everyone can see this object moving across the screen. And so it's moving from the left side to the right side. And we're getting these positional updates from the server on our game client. So first we get a message saying that the position is over here on the left side of the screen, then one in the middle, and eventually it receives another message saying that the object has moved to the right side of the screen. But you'll notice that even if we drop that second message and it never arrives, we know we're going to get another position update very shortly anyway. So the end result is the same. In other words, we're not really only interested in the current position, we're only interested in the current position, and we're not so much interested in where the position of the object was a moment ago. So for position, it doesn't matter all that much if we miss a message. Although again, I guess this kind of goes back to the not one size fits all sort of thing, because maybe you'll want some sort of mechanic in your game where you record where objects used to be, and then it's important to have those messages. So another case where it might matter if you get the message, or if you want guaranteed delivery, is for things that change less frequently. So for example, if the player's score in a tennis match changes, or if you're playing FIFA or something like that and you get a goal, it's pretty important that we get that information, because Usually at that point, we're going to want to increase the points for the player. We might play a cutscene or something like that to, show that we've actually scored a point. So in that case, in addition to guaranteed order, we might also want to offer guaranteed delivery sometimes. And that's usually how most, most game engines and networking libraries will handle this. So before I move on, I just wanted to stop for a quick moment here to see if anyone has any questions about what we've talked about so far. Hopefully my tea drinking isn't too loud for you all. All right. So we've talked a little bit about these network messages being sent from the server to the client. And a person might think that we might want to send messages as quickly as possible and as many as possible to keep things updating smoothly so we don't end up with, kind of a really low frame rate or something like that. Oh, sorry, before I move on, I do have a question here. Examples of these libraries, or is their name general category? So a lot of game engines will have these libraries kind of built into them, so Unity and Unreal Engine. If you're familiar with the Godot engine, it actually uses an open source library that you can look up, and that's called eNet, so just like the letter E, net. And if you wanted to take a look at it, you'll actually be able to see exactly how it implements all that guaranteed delivery and ordering and that sort of thing. Stayed for the tea drinking. So these network messages, as I was mentioning before, we might want to send them as frequently as possible and send as many as possible. But the problem with doing this is that it can actually cause network congestion for players with slow internet connections and increase their latency. So instead of sending these messages, say 60 times per second or 100 times per second, we might have the server send updates at a slightly lower rate. So here we maybe select only every second update to send to the client. But there's another issue that comes with this, and it might make movement look very clunky because we're getting these positional updates at a much lower rate than, say, we were on the top. So the top, we're getting, say, 60 updates per second, and on the bottom, we're maybe only getting 10 or 5 updates per second. And to get around that, we can actually use something called interpolation. And this happens on the game client. So let's assume that the game client gets an update for a position on the left side of the screen. And a little while later, we get another update, moving it to the right side of the screen. We can actually use math to perform linear interpolation, or what's also known as lerping, between two positions and then fill in the missing frame. So we get that middle frame there from running that calculation. So then we can actually get the same smooth movement, even with fewer updates from the server. So we've talked a little bit about the server sending data to the client, but what about the other way around now? And usually we don't want to send data such as our character's position or health, because this would allow cheaters to send fake messages. So if I were a cheater or a hacker, I could run a tool on my computer to send fake data to the server, saying something like, set my health to 100%. Or if I were playing, say, a racing game or something like that, I could say, my position is now right at the finish line. And this really ruins the experience for other players. So instead of sending this absolute data, generally the client is going to want to send input events instead, then let the server calculate the resulting game state. So for example, let's say we pressed a button to make our character jump. The client is going to send a message to the server to let it know that we pressed our jump button. Then the server is going to process that jump message, update the game state, and then it's going to send that player's new position back to them. And at that point, we can render that or draw it to the screen, and then we get our jump animation. So this is great. We don't have any more cheaters. But this actually comes with another issue, unfortunately. And the problem here is that it takes time for this to happen. So as I mentioned, I'm up in the Toronto area. And let's say that I'm sending a message to San Francisco. This message has to travel through several different cables, routers, and even the air if you're using something like Wi-Fi. And the longer, or I guess the farther distance that I have to travel, the longer it's going to take. So this ping to San Francisco from my home took 70 milliseconds. And at first glance, 70 milliseconds might not seem like much, but this lag is actually quite noticeable and it feels unnatural. So you can see here that if you're pressing a jump button, you have this slight delay before you actually get that visual feedback on the screen. And in this case, I'd probably end up in a pit of spikes or something like that. And if you're playing something like a competitive shooter, it can mean the difference between hitting your target and missing it entirely. So how do we get around this 70 milliseconds latency? Well, one of the things we can do is have regional servers. And the idea here is to bring that server from San Francisco to somewhere closer to me, so it doesn't take as long for my messages to travel there and for them to travel back to me. So what we do is before the match even starts, say in matchmaking, we do our best to group players together such that their latency is minimized. And in my case, I'd probably be matched against people in the Eastern US and Canada in a server in that region. So if you're an independent game developer, it might actually be hard to find budget to have regional servers, but there's something you might be able to leverage here. And this is an example, I guess, of a plot of online CSGO players at any given moment in time. And you'll notice, if you look at it closely, that the number of concurrent players actually doubles every 24 hours, and then it goes back down. So this is where you could leverage something like, say, Kubernetes with auto scaling, or the DigitalOcean API if you're running on Droplets, or any other cloud provider API as well would work. But the idea here is basically to have, a bare minimum number of servers, and then automatically scale up and back down when you don't need that, need those resources anymore. So this is great. We have servers everywhere, and I can play much more quickly with my friends in the Eastern US, and it's great. So I'll just stop here for another second to see if anyone has any more questions. I do see one in the chat here. The jump events need to be sent out of size of packets per second. Yeah, so generally, if you're doing something like a jump message, you'd want to send that immediately. So you wouldn't wait for that those messages that you're sending at a regular interval, like the positional packets. You'd want to send that immediately when you press the button, essentially. Yeah, that makes sense for sure. So as I mentioned, this is great. We can play with my friends in Eastern US and Canada just fine. But let's say that I want to play a game with my friend who lives in New Zealand now. We're still going to run into the same problem, right? Because my friend in New Zealand is very far away from the game server. And if you think about this problem for a little while, you'll eventually realize that the solution is kind of right under our noses. And that is to use something called client-side prediction. And the idea here is basically just to run the same game loop on both the client and the server. So when we press the jump button, we still send that jump message to the server, but we're also going to run those calculations on our local client, and then we receive that visual feedback immediately. Then when we get that server update back with the new position of our player, the position should be the same because they are running the same simulation. But if they're different for some reason, we can actually easily update our position with the real value. And has anyone here heard of the term rubber banding? I'm curious. Looks like we have a few other questions. I can answer those after we discuss this for sure. So I guess the issue with rubber banding is it creates a kind of a poor player experience because your player is going to be teleported either forward or backward or in a different direction. And this client-side prediction is actually what causes rubber banding. So your client thinks you're in one position, but then it has to quickly reconcile its position with the server's data when the server sends its update. And this usually happens usually when you encounter a really big lag spike. So if your ping really increases, if you're on an unstable connection, or if you have some packet loss. So if those messages get lost somewhere along the way. Okay, so far we've talked a little bit about interpolation, regional matchmaking, and client-side prediction. So what we want to do is reduce latency by using interpolation and regional matchmaking as much as possible. And then when we use client-side prediction, we can do that to help mitigate the effects of any remaining latency. And what I can do is I'll go back and try to answer some of these questions I think I saw in the chat here before we move on. So I'm just scrolling through. So about playing with people from other parts of the world. Yeah, that's definitely an issue. And that's, we discussed that, I think, with the New Zealand part. How long does it take to spin up a droplet? Generally, I think in the past, it's taken somewhere between 30 and 45 seconds, I think, to create a new droplet. But don't quote me on that 100%. I think generally in that time range, though. Can I just send these data to clients without processing in the server? So so you could do something like a peer-to-peer connection. So rather than having a client to server architecture, what you would do is you'd have each client connected directly to the other clients, and that way your messages aren't going to go through the server. But then you do run into some other issues. So a lot of games do have a client to client, so peer-to-peer type architecture, and we're actually going to discuss one shortly here. But yeah, the issue there is that it opens up the potential for more cheating and also potentially less stable connections. If you did want to use something like blockchain, I'm not super familiar with blockchain and how long it takes, but generally I think for video games we stick to more simple protocols, just UDP, because we want those actions to happen immediately. If you were playing a slower paced game, maybe you could use something like blockchain. And let's see if there's anything else. Even with small lag, wouldn't the server position always be a little bit behind the client's position due to the lag? That's actually a very good question, Eric, and I think I will be discussing that shortly here. So, if I don't answer your question in the next few minutes, definitely make sure you re-ask the question, and I'll try to get it to it then. Best practices in memory management, for example, clients disconnect unexpectedly. Um, so it's going to depend on the game. Sometimes, if you have a game and you want to make sure that all players are always connected, if someone disconnects from the game, you might just say the game is over, and then you can clear everything from memory, and the other player won. Or if you have a game where multiple players can be playing at the same time, and you have people join and then leave, and then someone else join and leave, and then that other person that left before might come back. It becomes a little bit more complicated, but um, I guess it depends. It really depends on the game, I think, on whether you want to keep their information around for later if they rejoin. So if you want to keep their score in that match, or if you want to clean that up as well. But yeah, generally you're just going to want to clean up the sockets that are lying around. And if you do want to clean up their scores and player model and that sort of stuff in the world as well, then you can do that too. So I guess another question would be, does DigitalOcean offer any products or features that are helpful or better for game servers? And I would say that one of those is definitely Kubernetes. If you do um, if you do want to run on Kubernetes, DigitalOcean has a great platform, and it does support auto scaling as well. So if you did want those regional servers, you could have them all over the world and have a small cluster, and then add more servers as you need them, as you have more players playing concurrently. And then I think I missed a question a bit earlier, which was about encryption as it relates to UDP and TCP. And thankfully, with TCP, there's a standard known as TLS, and that's kind of baked into a lot of different libraries, so you don't have to worry too much about that. I mean, you still have to generate certificates and that sort of thing to prove your identity, but for things like matchmaking and say chat data, or sending, like if you have microtransactions or something in your game, you'd send that all over TCP usually and use TLS. In UDP, there are ways to encrypt UDP packets, but generally it isn't used a lot in games just because it takes a lot of extra time. And you could be sending that information over TCP instead. So for things like positional updates and like those jump messages, we usually wouldn't encrypt those. Since Kubernetes can preempt your running container, how do you ensure that clients don't experience lag due to normal Kubernetes operations? Yeah, so I guess in this case, um, you'd want to make sure that your games, um, I guess that's another case of you know, one size doesn't fit all. So if you were using Kubernetes, it'd be best to kind of gear it towards games that have shorter play sessions, so you don't have to worry about that running into that situation as often. If you wanted to have longer play sessions, maybe having full virtual machines or droplets spin up on demand might be a better solution there. Okay, so I think that's it for now. Hopefully I didn't miss any. I might have, but I can stop again at the end, and if people have more questions, we can cover those as well. So we talked about client-side prediction, and that works fine for things that we can simulate locally. So things like our player's own position, or things that follow specific trajectories. So say a tennis ball, or like if you throw a grenade or something like that, it has a very specific trajectory, and we can use math to calculate where it's going to be. Another example might be, say, an airplane kind of flying in a straight line, and we can calculate where that's going to be. And that's actually a technique called dead reckoning in multiplayer development. But something we cannot predict is another player's movement, because we don't actually know their position or where they're going to move until we receive it from the server. So we're going to take a look at Splatoon, which is a game where your goal is to paint the environment and players on the opposing team with what are essentially ink-filled water guns. Now, as a disclaimer, Splatoon actually uses peer-to-peer architecture rather than having dedicated servers. So what we're about to discuss doesn't apply completely and directly to Splatoon, but it does apply to many other games. So I thought it would be a good example to have this visual representation. So let's imagine an enemy running to the right side of the screen, and you're trying to hit them with some ink. Your game client is getting updates from the server with the enemy's position. But these updates, as we've discussed earlier, actually take time to travel from the server to the client. And since we can't use prediction, we're actually seeing the enemy's position in the past. So when we press the button to shoot at the enemy, that message also takes time to travel to the server. And you can see here that this is a problem, because by the time the shoot message actually reaches the server, the enemy is nowhere near the position you see on your screen. So we're aiming way over to the left of where the server actually thinks the enemy is. And that's where we're actually running our hit detection algorithm, which is on the server. And our shot is, we're going to miss. So one thing we can do, I guess, is to consider client-side hit detection. So we let the client tell the server that we hit the enemy or that we missed the enemy. And this is usually what something like a peer-to-peer game would do. So as far as I know, this is actually what Splatoon does. And as I mentioned, that this kind of opens you up to cheaters, because they could send a fake message saying, I hit the enemy or I hit you, even though they didn't. They might not even have line of sight with you. So you can see that being a problem. A lot of games can get away with this because they're running on consoles rather than PC. And it is a lot harder to cheat in consoles just because they're a lot, like their memory models are a lot more locked down than say a PC would be. So rather than having client-side hit detection, another solution is to have the game server compensate for this delay. Let's say an object is moving, so we have our enemy again, moving from the left side of the screen to the right side of the screen. One thing the server can do is take time-stamped snapshots of the object's position. So it ends up keeping a history of the game's state as the enemy moves from the left side to the right side of the screen. And what else can we do? Well, the server, I guess, can keep track of the player's current ping. So when it actually gets that shoot message from the client, it's able to calculate how far back into the game's history it needs to go before running the appropriate hit detection logic. So for example, if we have a ping of 30 milliseconds, the server knows that we pressed the shoot button 30 milliseconds in the past. But before we run the hit detection algorithm there, the server also knows that when you press the shoot button, your game client was drawing the enemy 30 milliseconds behind its actual position on the server. So then at this point, this is where we would actually run that hit detection logic. So usually hit detection is going to be something like casting a ray through a bounding box of the object to see whether they intersect. And that's about it, really. Game development and multiplayer game development are kind of huge topics, and I don't want to get too into the weeds of technicalities. But if anyone does have further questions, I'm happy to answer them. So I wanted to keep this a little bit kind of short and sweet. But the key takeaways here are to reduce latency as much as possible. And then when we can't do that, we use techniques such as client-side prediction and lag compensation to mitigate its impact. So that's it for my content, I guess. But yeah, I'll take a look at the chat here to see if anyone has more questions. Which language do you recommend for game development? So it really depends. I think whatever you're comfortable with is probably best. But if you want to squeeze, every bit of performance out of a system, C++ is kind of the tried and true way to go. But for most kind of indie games, that isn't typically necessary. And using something like Unity's C# or Godot has their GD script is great as well if you're looking for an open source game engine. And they're both plenty performant for most cases. You'll also be limited, I guess, a bit by the platform you're targeting. So if you're wanting to make a game for PS4 versus PC, but and then again, a lot of those engines will handle that for you as well. If all clients agreed on a hit, doesn't that mean it really hits and there isn't any cheats? Yeah, so that's another thing you can do. That's actually in one of the games I worked on in the past. We did something similar to that for the peer-to-peer connections, and in most cases it does work well. But then you run into an issue of what happens if not all players agree on the hit. You could have, one bad actor that always says hits never hit unless it's their own hit. So, so you do kind of have to think about that sort of thing as well. And there are trade-offs of going one way versus the other. But again, one size doesn't fit all. So it really depends on the game you're making. Another, I guess, advantage to client-side hit detection is that it puts less strain on the server. And also with peer-to-peer connections, you're not paying for that server infrastructure as a game developer. With respect to lag compensation, do most games try to compensate for buffer bloat related issues? I'm not sure. I think, could you elaborate on that question? I'll have to come back to that, I think. As far as my background goes, though, I've worked at Ubisoft in Toronto in the past. So before that, mostly working on network programming sort of things. And then when I did move over to Ubisoft, I was working on their network team as well, and worked on Watch Dogs 2 and Watch Dogs Legion there while I was working at Ubisoft. Can a CDN such as Cloudflare reduce the latency? So CDNs usually distribute cached data, and because games are inherently very dynamic, so things are changing a lot in them. A CDN probably isn't a great fit for games, although for other games, like less fast-paced games, or some games, I guess, it might work, but I haven't used it in the past myself. How do WebSockets in JavaScript compare with TCP or UDP? So WebSockets in JavaScript use a TCP connection over HTTP. So, so if you're making like a browser-based game, that will generally be a TCP connection. Although I think there have been some experiments with using, oh geez, there are new ways that you can actually have peer-to-peer connections in web browsers, and that will use a UDP or send UDP packets. I haven't looked too much into that though. It's been a while since I've done kind of involved front-end development. What is the most difficult kind of game to implement online multiplayer with? I think, I guess each different game kind of comes with its own challenges. If you're playing something like a large kind of open world MMO, it can be difficult synchronizing game state between clients. So let's say you have two different players and one is much more progressed than the other player. They might have certain areas unlocked and the other player might not have those areas unlocked. So how do you reconcile that state between the two if they start playing together then? Like a gate might be locked for the other person when it's open for the other person. So it doesn't necessarily come down to kind of performance issues or anything like that, but there are a lot of kind of tricky problems like that you have to solve as well. Would the client ever try to predict the enemy's location by extrapolating? So I guess that kind of comes down to the client-side prediction. And in some cases, we actually can try to predict the enemy's location. So in stuff like first-person shooters, generally it doesn't work as well. But if you're playing something like a racing game, cars usually follow a pretty specific path. So you can predict a little bit to try to smooth out their movement. And that's using that dead reckoning technique that I mentioned earlier. Independent developers, most cost-effective option to get sandbox or staging environment on DigitalOcean. Yeah, so I'd probably recommend using just single droplets to get started. And then if you need more than that, you can spin up more droplets. Or if you want to get more advanced with auto scaling, that sort of thing, you can use the DigitalOcean API to do that, or you can try switching over to Kubernetes. But that Kubernetes jump is definitely quite a big one. There's a bit of a learning curve there for sure. Recommend further resources to drill down into takeaway topics. So a really good resource is actually the Valve developer. I think the Valve developer wiki. They have some good a good write-up on how their I guess hit detection, that sort of thing, and light compensation works in CS:GO and Half-Life. So if you take a look there, that's great. Riot, so the League of Legends creators, they actually also have a really great dev blog that you can take a look at there for more info. WebRTC, yes, definitely. I think that's actually the word I was looking for earlier that completely slipped my mind with more kind of web browser-based games. I think that's what a lot of kind of newer browser-based games are experimenting with now. And Rust, yeah, Rust is definitely another great language. I think there's I'm trying to remember the site now. I think it's Are We Game Yet? And that one has a list of different Rust game libraries that you might be able to use. So they aren't quite as mature as, say, C++ libraries would be, or using an engine like Unreal or Unity, but they're definitely out there and they are getting better. Do you have any plans to dive on each point in the takeaways? Ready to go much deeper. So unfortunately not in this talk, but I mean, if this talk was well received, maybe I will have to do another one where I dive in a little bit deeper to some of these topics for sure. But yeah, if you do take a look at, say, that eNet library or the Valve developer wiki and the Riot Games blog, that's a good place to start for sure if you want to go deeper. I'm trying to see if there's anything else I haven't covered yet. Having larger buffers can increase latency substantially, up to a second or more, by using some sort of queue management. Those latencies can be reduced to a much more tolerable amount. Yeah, I guess you probably wouldn't want to buffer a ton of data in games, because yeah, like you say, you do end up with that added latency. So it kind of becomes, I guess, a balancing act of how much data you do need to send out at how frequently of an interval. And I guess some things you can actually do to help mitigate that is to use kind of simple forms of compression, I guess. So rather than always sending the full player state or full game state to players at a specific interval, what you can do is you can only send them the things that have changed. So that really reduces the amount of data that you have to send. Another thing you can do is actually, like if you're, say, playing a larger kind of more open world game, or if you're playing something like PUBG where you have a much larger map, you can break that map up into different partitions, and then you only need to send the data. I guess you can kind of keep the data local to each partition. So if you have 5 players in one partition way over here on one side of the map, and then another set of players over here, you don't need to send the same data to both because these players aren't really going to be able to interact with each other anyway. So you can save a lot of data that way too, and keep your buffers a lot smaller than they would need to be otherwise. Any starting resources you recommended? So as a web developer, I think, yeah, those resources that I mentioned before, definitely. The Valve Wiki and Riot Dev blog are good ones. I think, I'm trying to remember now, I think Unity and Godot probably also have some kind of tutorials that you can go through on their sites or through the manual for those engines, and they can kind of get you started as well, just to kind of see how things work together. Should the server ever trust a timestamp generated by a client when a jump command happens? So yeah, I guess that's kind of a really good constraint to have when you're developing multiplayer games, is to trust the client as little as possible, because they could be cheating. So in most cases, you can trust, say, something like an input event from the client, and you can actually run some validation on it as well. So if the server has a message come in that says the player jumped, you can kind of look at the timestamp they have and see whether it makes sense. So did they jump a minute in the past? And if they did, then we're just going to throw that message away and say it didn't happen. Or if they're jumping in the future, or if they're jumping kind of in the future even lower than what their latency currently is, then is usually a sign that they might be trying to cheat as well. Arda, thank you for that link there. Definitely. Yes, Rob. Yeah, Godot is, for new developers, Godot is great. The syntax is a lot like Python if you're familiar with it. And don't be discouraged or kind of set off or put off by it because of that. It is still very performant. It uses C++ under the hood. And like I said, that eNet library for multiplayer and networking. And you can actually write in native C++ as well if you do want to squeeze extra performance out of it. How many clients should you have connected to one droplet? It really depends on the type of game you're playing or type of game you're developing, I guess. If it's something like a first-person shooter and you have a lot of different things going on, like a lot of bullets, a lot of different objects moving that you need to do physics calculations on, you're going to need a much larger droplet to handle that workload. But if you're playing something like chess or slow-paced where there isn't a lot to calculate, you could probably handle thousands of players just on, say, a $5 droplet if you program it properly. Yeah, let's see if there's anything else. Hopefully that's all the questions. Hopefully I didn't miss anything. Dive deeper. Would definitely love to, but perhaps another time when we have a little bit more time to discuss things. Sorry if my voice is starting to go. It's with the COVID lockdowns here. It's I don't have to talk as much as I usually do, so I'm not used to it. Yeah, actually, another cool thing is Godot will actually you can compile it and target it to the web. So if you were to write a game in Godot, you write the game once, and then you can deploy it for PC, and then for web as well, and for mobile. And the web version actually does use WebSockets then under the hood. So it'll do that all automatically for you. I'm pretty sure Unity will have a similar sort of thing. But I'm trying to advocate definitely a lot for Godot because it is an open source game engine, and I think it's a great tool, and more people need to become aware of it. So I think that might be it. I don't know if anyone has any last minute questions. Cool. Well, I suppose if that's it for now, I definitely really appreciate you all joining me today. Had a lot of fun here, and I hope you all learned something. It's always tough, kind of getting the balancing act of going, too deep into things and keeping it, understandable for those who just kind of want a taste of what game development and multiplayer is like. So yeah, I hope the rest of your week goes well, and thank you again, everyone.